I'm attached to the Sunway University and in the center, BECCS Center on Sustainable Development. And I've been here for about 7 years. And before this, I was in the University of Malaya for more than 45 years. Now, I will be talking to you today on sustainable carbon sequestration challenges and future pathways. Basically, the focus will be on biomass, although I have touched on other related areas. And the carbon sequestration will be the main discussion point. Now, since I am not so familiar with the members who are attending this talk, what I want to do is if you look at the my table of contents, I will be starting with some very basic introduction to carbon sequestration, so that I think everybody is in line, so that everybody follows what we are going to discuss for the next 40 minutes. So I will look at the types of carbon sequestration, and then natural or biological sequestration, soil carbon sequestration, which is very important in agriculture, bokashi, composting, and composting contributions, carbon sequestration technologies, and then we go on to global potential and statistics and what is its impact on climate change and so on. And carbon sequestration in agriculture, we will be looking at the opportunities and co-benefits of carbon sequestration, and we come to our conclusion. So let me start with something very basic. What is carbon sequestration? I think the first line clearly explains that carbon sequestration is the process of capturing and storing atmospheric carbon dioxide to reduce the climate impact. I think this is the key line that we should understand. So we are trying to capture the carbon dioxide, and then we use various methods to store the carbon dioxide so that we could reduce the atmospheric carbon dioxide. And why do we have to do this? It is essential because carbon dioxide contributes about 76% of global greenhouse gas emissions, mainly from fossil fuels, agriculture, and waste. Now, look at some numbers which I'm giving here. Why carbon sequestration matters? Globally, greenhouse gas emissions, about 53.8 gigatons CO2 equivalent per year. And the CO2 contribution itself is 76% of the total emissions. Agriculture's share is about 18 to 22%, including soil degradation, fertilizer, and livestock. And the waste sector emits about 3 to 5% of global greenhouse gases. Well, in some references, it is given up to 8% comes from the waste sector, mainly from methane from landfills and anaerobic waste treatment. So the diagram illustrates what I'm just telling you. So the carbon sequestration, the various methods that we use for capturing the carbon dioxide and storing the carbon dioxide. So this will be our main discussion from now on. Now, why is carbon sequestration important? The natural or biological carbon sequestration, which includes, of course, this is taking place in the forest, grasslands, wetlands, and so on. And the forest absorbs about 7.6 gigatons CO2 annually. So this is God's treatment of capturing carbon dioxide. Soil carbon sequestration practices like in the bokashi method, or Biochar method, and so on, is about 0.4 to 1 ton of carbon per hectare per year. So you can see the scale based on the how big the acreage is. Biochar is capable of locking carbon in soils for hundreds to thousands of years, sequestering up to 1 ton of CO2 equivalent per ton of biomass. So I think this is the gist of what we need to know. 1 ton of CO2 equivalent per ton of biomass can be captured. Now, of course, we can Also use engineered or technological carbon sequestration, which includes carbon capture and storage, direct air capture, or biological carbon capture and storage, and geological storage. Now, carbon capture and storage facilities currently capture about 50 million tons or zero point 0.5 gigatons or CO2 per year. Direct air capture technology has the potential to remove up to 5 gigaton of CO2 annually by 2050 if scaled. So these are the options we have. So types of carbon sequestration, very briefly. Number one, terrestrial sequestration. So this one stores about 30% of the global CO2 emissions, which includes the forests, plants, and soils, which is very, very important for managing the carbon naturally. Soil carbon, these soils hold about 2 to 3 times more carbon than the atmospheric, and regenerate practices, uh, regenerative practices can increase soil organic carbon by about 0.4 to 1% per year, equal to about 1 to 3 tons carbon per hectare. Geological sequestration can store about 1,000 for about 1,000 years. The current global carbon capture and storage capacity is around 50 to 60 million tons of CO2 per year. Ocean sequestration, which is another big area. Ocean absorbs about 25% of the annual human CO2 emissions. Blue carbon ecosystems like mangrove, salt marshes, seagrass, and stone up to about 10 times faster than forests. So this is one of the areas of concern because people try to use the mangrove areas and then convert it to aquaculture and so on, but thereby removing the mangroves from many, many countries. Now, technological sequestration, we are talking about direct air capture, which removes about 1 to 10 million tons of CO2 per year globally. Uh, this is a growing sector. And then the biological carbon capture can achieve net negative emissions, removing 2 to 5 tons of CO2 per ton of biomass, depending on the system efficiency. So we can actually depend very much on the biological uh, carbon capture. So on the right, the diagrams depict what I just told you. So we have biological sequestration, terrestrial sequestration, ocean sequestration, geological sequestration, chemical sequestration, direct air capture, carbon compression, carbon transportation, and carbon neutral. So basically, the pictures describe what I just mentioned. And once again, types of carbon sequestration continued. We are talking about reinforcing the idea. Sequestration, carbon stored in plants, microbes, and ecosystem. Geological sequestration, injecting carbon dioxide into deep underground rock formations. Carbon compression, compressing captured carbon dioxide into a dense transportable form. Terrestrial sequestration, carbon stored in forests, grasslands, soils, and wetlands. Chemical sequestration, here we are talking about mineralization, can lock CO2 permanently within the waters, and carbon transportation. Ocean sequestration is about 9.2 to 10 gigatons. And this is the percentage of global human emissions is about 26 to 30%. Okay, so, and then forests, all types of forests can capture about 30% of the global human emissions, like tropical forests. And then soils, of course, can absorb about 2.6 to 5 gigaton. That is about 10 to 15% of the global human emissions. And grasslands, about 5 to 7% of the human emissions. And lastly, wetlands and peatlands, about 0.5 to 1 gigaton CO2 per year, which is about 2 to 4% of the global human emissions. Yes. On the right, I've given the diagram of the various parameters which I just described. Now let's look at soil carbon sequestration. Soils store about 3,000 gigatons of carbon, which is about 3 times more than the atmospheric and 4 times more than all living plants. So soil holds 45% of the terrestrial carbon globally. So global agricultural soils can sequester 1 to 1.5 gigaton of CO2 per year with root practices. So reforested and restored soils can remove up to about 3 gigatons of CO2 per year. See, the 4 per thousand initiative aims to increase soil carbon by 0.4% per year in 20 to 30% of annual global carbon dioxide emissions. So we are looking at the soil organic carbon levels, which vary depending on the soil type. Like for example, in the degraded soil types, 0.2 to 1% of soil carbon. In healthy agricultural soils can capture about 2 to 5%, and forest soils about 5 to 12% of the soil carbon sequestration. So each 1% increase in the soil organic carbon stores around 20 to 30 tons of per hectare, equivalent to 73 to 110 tons of carbon dioxide per hectare. So you can see the intensity and the relevance of soil carbon capture, which is being practiced naturally as well as artificially. This diagram, if you care to look at it for maybe a minute, will actually summarize what we have been talking up to now. Number one, the point number one, plants absorb carbon. I think everybody knows this. And via photosynthesis, they capture the carbon dioxide to build organic compounds for plants' growth and health, which is the basic requirement of the environment. If there is no photosynthesis, I think CO2 absorption will be almost zero. And the two, roots take up water and nutrients in partnerships with soil organisms such as nitrogen fixers and so on. And then the third one, the decomposition of the organic material, such as, and of course, we can also use it for heat production. And any CO2 produced is back absorbed by the plant. On the other hand, we produce biochar from the pyrolysis process, which is used directly onto the soil. And this it is able to sequester the carbon, reduce the fertilizer intake, and mitigate methane and nitrous oxide. So this is one mechanism for agriculture. And further continue on the agricultural practices. The conservation systems boost soil carbon and crop productivity, and carbon sequestration stores carbon long term, reducing carbon dioxide. I think this by now, I think you should have captured this point. Key sources will be the trees and perennial roots and stable soil organic matter. Soil organic matter can stay stable for centuries in micro aggregates. Adoption across 64 million acres in the southeast US could store 47 million tons, I think, and a reduced tillage lowers fossil fuel emissions by 20 pounds carbon per acre per year. Now, on the right side, once again, I'm giving you the flow of the carbon in agricultural practices. And as I mentioned earlier, so we have the carbon cycle that is being captured in photosynthesis and so on, and then it's being released as biomass, and it can be used again in the production of biochar and so on. And one more thing about agricultural practices, and let me look at the diagram on the right side. Look at the diagram on the right side. Carbon farming, global carbon storage. Sequestration possible in soils 4 to 5 gigatons of CO2 per year, but this is possible. But the sequestration needed to meet the 2%, 2 degrees centigrade goal is 15 gigatons CO2 per year. So you can see that we are at least 3 times not within the target. What we are doing now is only for 4 to 5 gigatons, but what we need is at least 15 gigatons sequestration needed to meet the 2% centigrade goal. And current emissions is about 41 gigatons of CO2 per year. So it's so much higher that we need to seriously observe and tackle the carbon emissions. So recent years are the hottest on record. CO2 is at its peak. That's what we realize now in the recent climate conference. It can store an additional 42 to 78 gigaton if improving the fertility, structure, and water retention. So we can play with these parameters to increase the carbon capture. Soil is a major carbon sink, and it supports plant life and hosts billions of microorganisms. And healthy soil boosts yield and removes the carbon dioxide. So the key practices is reduced tillage, cover crops, compost or organic amendments. Now this rebuild the soil organic matter, increase productivity, reduce erosion, and improve climate resilience. Food waste is thought to produce about 8% of the global emissions. 33.7% of produce is unharvested. So we can go into this food waste and talk the whole day, because if you look at where the food waste is generated and how it's being treated, you will be surprised that right from harvesting, transportation, manufacturing, packaging, every stage produces food wastage. And of course, some countries have started to tackle this so that they can increase the productivity and reduce the famine in the world. But it is a reality that we still have a very serious percentage of food waste being generated in many countries, and even developing countries, it's a big issue. Now let's move on from the agricultural carbon sequestration to geological carbon storage. Here we are talking about saline aquifers, which represent about 60 to 80% of the global CO2 storage capacity. Estimated potential is 1,000 to 10,000 gigatons worldwide. It's possible. Porosity typically about 10 to 30%, so allowing large CO2 absorption and CO2 stored through structural, residual, solubility, and mineral trapping. Another area that we can also consider when we are talking about geological carbon storage is the depleted oil and gas fields, which sometimes is just abundant. It can be potentially used for carbon storage. Accounts for about 20 to 30% of storage potential. The potential is there. It is proven safe. Hydrocarbons stayed trapped for 10 to 100 million years. Existing infrastructure can reduce project cost by about 25 to 40%. So if we were to use the existing structure that has been abandoned, when there is no more oil there, the structure can be used and we can save up to 40% of the project cost. When combined with EOR, 20 to 40% extra oil can be recovered while storing CO2. So this the extra oil reserve can be recovered. 20 to 40% extra oil can be recovered while storing CO2. So on the right, once again, I'm giving the same thing in the diagrammatic form. So we have the atmospheric carbon dioxide, which is coming from the emissions and so on. It can be uptake from the soil or from the plants and so on. Use of carbon dioxide in EOR, leakage through faults, reaction with concrete and so on. So eventually these are captured and the chemical formula is given right at the bottom, where CO2 can be converted into bicarbonate and so on. So it can be stored in that form in the saline aquifers or depleted oil and gas fields. Now, this diagram actually gives an overview of the various blue carbon sequestration. So the overall picture is given here. So we can start from on the left. We have the adaptive benefits, ecosystems protect from erosion and reduce flooding from sea level rise. Then we have respiration, release CO2 and other greenhouse gases such as methane and nitrous oxide. Photosynthesis transforms carbon dioxide into plant biomass. And then habitat destruction releases carbon dioxide back to the atmosphere. So I think this is one of the concerns that we need to address. Habitat destruction for various reasons, aquaculture or land reclamation and so on. Restoration permits carbon dioxide uptake into new biomass. So then we have various salt marsh or mangrove forests, seagrass, so on. And carbon sequestered. And habitat restoration also gives us extra storage. So this is a sort of overview, but non-quantitative way of telling how much we can benefit from the blue carbon session. So in summary, blue carbon ecosystems, we are talking about coastal ecosystems that capture and store carbon. In mangrove, for example, the soil tolerant trees and shrubs with about above ground roots that grow in intertidal series of tropical and subtropical coasts. Then we also have seagrass, aquatic flowering plants with grass-like leaves that grow in shallow coastal waters, forming underwater meadows. Then we have salt marshes, coastal wetlands, regularly flooded by tides, where soil-tolerant grasses and needs grow. So can grow on mud and peat soils. So these are some of the options we have for blue carbon ecosystem. Now let's move on to technological carbon sequestration. So let's look at direct air capture. And this is quite a simple mechanism. Now, before I discuss the numbers on the left, let's look at the mechanism on the right. Now, the fan draws in the air. So basically it's a big suction. And then it goes to the filtering system. Now, the filtering system filters the carbon dioxide and releases the carbon dioxide free air out without the CO2. And the CO2 that is captured is heated to release the captured carbon dioxide. And it can be either released CO2 free air, and the carbon dioxide is captured in cylinders and can be used for commercial purpose. So it's quite a straightforward kind of mechanism, carbon capture from the air. Now let's look at the numbers. Now, direct air capacity, the direct air capture capacity in last year was 0.1% of annual globe emissions. Expected capacity by 2030 is about 60 to 100 million tons of CO2. It's about 0.15 to 0.25% of global emissions. It's still quite lower. Potential by 2050, maybe 1 to 2 billion tons of per year. It's about 2 to 4% of the global annual emissions. Energy use requires about 1,200 kilowatt hours of heat or electricity per ton of CO2 captured. This may be the negative aspect of this mechanism. We need a lot of power, 1,200 kilowatts of electricity. Costs about 200 to 600 US dollar per ton. And this is projected to decrease to about 100 to 150 US dollar per ton by 2050 when we improvise the mechanisms and make it more efficient. So that's the bioenergy with carbon capture and storage. So here we are talking about the biomass. So carbon on the right side, the diagram shows the carbon dioxide is captured and the CO2 atmospheric draws down, and then the biomass residues we can use it together with waste in waste to energy plants, and the CO2 capture and transfer and storage. Here they are talking about underwater storage, and the bioenergy combustion or biofuel conversion is used for the industries and household. So it's a straightforward kind of biomass utilization by transforming in the waste to energy plant. So biomass turned for energy, CO2 captured and injected underground, provides net negative emissions if biomass sustainably sourced. Okay, if the biomass is sourced sustainably, we may record net negative emissions. Global mitigation potential is about 0.5 to 5 gigatons of CO2 per year by 2050. That's about 1 to 10% of the global emissions. Energy contribution can supply about 5 to 10% of the global electricity while removing carbon dioxide. Capture efficiency is about 85 to 95% of CO2 from the biomass flue gas. So this biomass mechanism seems to be one of the most practical and most optional way of capturing carbon dioxide with such a good record of net negative emissions and so on, and at the same time producing green energy from this method. Now, this is carbon capture and storage at industrial sources. So here again, let's look at the diagram on the right side. So we have industrial production, and we use carbon capture, which any one of the methods, and then the CO2 is compressed, and then a CO2 injection into the this is underground storage of CO2. So carbon captures CO2 from cement or steel or petrochemical plants, power plants, which are the big players in producing carbon dioxide. Current global CCS capacity is about 49 million tons CO2 per year. It's about 0.12% of the global emissions. By 2030, it's expected that 400 to 500 million tons of CO2 per year, that's about 1 to 1.2% of the global annual emissions, may be achieved by 2030. Capture efficiency is about 90 to 98%, depending on the technology. Most feasible for hard to abate sectors like the cement industry, for example, 7% of global CO2, steel about 8%. So it can be done depending on what kind of mechanisms that we want to use and how is the costing of the carbon sequestration. Now, mineralization or enhanced weathering and carbon mineralization, this is sometimes is even can take place naturally. CO2 reacts with rocks, basalt, and olivine and forms stable carbonates. Its permanence is more than 10,000 years, 100% long-term stability. Potential carbon removal by 2050 to about, it's about 2 to 4 gigatons of CO2 per year. That's about 4 to 8% of the global emissions can be done by this mineralization. Energy requirements vary, but crushed rock spreading costs about US $50 to $200 per ton of carbon dioxide. So this is given in the diagram on the right side. Basically, it's naturally taking place mineralization to capture CO2. And then another one is the ocean alkalinity enhancement. So here we are adding alkaline minerals to seawater to increase carbon dioxide absorption capacity. Removal potential for 2050 is about 1 to 4 gigaton of CO2 per year. That's about 2 to 8% of the global emissions. Stability is about 90%. This is the long-term system, but requires monitoring to avoid ecosystem. So I personally feel that this method has to be done very cautiously, because by making the ocean alkaline, we may inadvertently play with the flora and fauna in the ocean, and we should be monitoring it very carefully. So this is why we need requires monitoring to avoid ecosystem impacts, so that we don't want to create another problem by absorbing CO2, but and they're offsetting the flora and fauna ecosystems negatively. So we have to be careful with that one. Now, global global role of technology-based sequestration, combined potential by 2050, we can talk about 10 to 20 gigatons per year. That's about 20 to 40% of the global emissions. Is essential for achieving net zero by 2050, especially for aviation. Is about 2.5% of global CO2. Shipping, 3%. Cement and steel industry, 15%. And the current cost is high, but it is expected to decrease by 30 to 60% by 2050. So we are talking about various options that's it's practical and possible, but sometimes the cost may be a factor. And well, we know that like aviation and shipping, actually these are the industries which is increasing in their requirement, which means their release of the emissions will also increase accordingly. So we need to tackle it very systematically, so that it doesn't negatively affect the aviation or shipping industries. Okay, now decarbonization. This is another thing that I just want to touch a little bit. So here we are talking about technologies and gaps in deep decarbonization of hard to abate industrial sectors. So we have been talking about deploying the most readily achievable opportunities, like process and enhancement or energy management, high strength materials. On that, this is in the early days 2020, but now we are talking about accelerating the deployment of zero carbon technology. So we need to play with the technology itself. So, like for example, lightweight design or material recovery and so on, lifetime extension, biomass gasification. So we have many options there. And then the future, large scale deployment and disruptive tech innovations. We are talking about, for example, the e-curl substitution with disruptive materials, or we are talking about hydrogen with CO2 from BAC as feedback. So these are the options we have for decarbonization. And we can see how it's evolving from 2020 to 2030, 2040, and then 2050, and thereby reducing the need for carbon dioxide. Now, bioenergy with carbon capture and storage, this is another thing, but we actually touched on this earlier. So we have the photosynthesis taking place, carbon sequestration, and then the bioenergy, carbon capture and storage in the various and permanently storage in geological reservoirs. We've seen this. Clean energy in the decarbonization transition of multi-sectors. So here we are, this diagram actually gives you the clean energy in the decarbonization transition of multi-sectors. So there are many sectors I put together here, like for example, building sector, wind energy, solar energy, hydroelectricity, building sectors, transportation, and then we are talking about electrification, water, transportation sector. So there are many sectors which actually gives us clean energy without generating carbon dioxide. So this is another option that we have to explore to not to produce CO2. This slide, I think, is a little bit like a case study strategies for decarbonizing bioethanol production. So we can have process improvement, carbon and utilization, or we can use carbon capture and storage. So which we were discussed all this before. So this is for ethanol production. So this is again decarbonization in the bioethanol system. Which I will not actually go through in detail mechanism. So you can have a look at this. And one more slide on the decarbonization of bioethanol production system. Um, cornerstone of decarbonization. There is tremendous potential in biomass utilization, which I will personally say that is very underutilized. The capacity is there. So biomass contributes about 10 to 12% of the global primary energy supply. Modern bioenergy is about 6 to 7%. Global technical biomass potential is about 150 to 200 uh, gigajoules per year, could meet about 25% of the world energy demand by 2050. So the potential is tremendous if we want to use biomass to produce energy sustainably. Sustainable agricultural residues like rice straw, palm fronds, bagasse, and so on can give up 5 million tons per year. And bioenergy could reduce CO2 emissions by 1 to 2 gigatons per year by 2050 with advanced conversion systems. Now, on the right side, you have some numbers, regional examples where the biomass is being generated. Like in Malaysia, okay, so one of the requests is that the slides should be shared. And I think what I will do is to send the slides to the organizers and let them decide to share the slides after my presentation. Okay, now what I'm trying to say here is that the potential is tremendous, but in Malaysia, unfortunately, most of these is about 15 million tons per year from rice husk, jute, and livestock. We can go on giving you the whole list of biomass, but the thing is, um, many countries are not realizing the potential of biomass utilization. So this is the sad part of this. So this is how we should awaken the need for biomass utilization and carbon capture. Okay. These are some extra strategic role for biomass utilization, decarbonization, recovery resource, policy alignment. Um, oh, they're asking for the slides again. Okay, okay. Why is it not going up? Okay, where are we? Yeah, we were here. Now, those who want to have these slides, I think you should contact the organizers because I'm not going to send the slides to individually one by one. I can send the slides to the organizers and then let them contact you. Okay, so let's move on. So here we have numbers on biomass utilization. There is a great potential. That's what I'm trying to say here. Great potential in utilizing biomass and greenhouse emissions, about 57 gigatons CO2 equivalent waste in agriculture sector. So we can use and offers up to 25% of the energy. Now, this is biochar for soil and carbon sequestration. Relatively, a lot of people are now studying on biochar, and it has become one of the most important area of research. How we can use, instead of using the plant material directly, we can convert the plant mass using pyrolysis into biochar, and then we can use it in the soil for CO2 sequestration and so on. So this is becoming very, very attractive and very popular. And then biochar's role in soil improvement, carbon sequestration, and emission reduction. So this gives you the mechanism of CO2 capture during photosynthesis, plants uptake and CO2, and then we have the whole thing going down to the roots. So biochar amendment actually enhances the carbon capture in the soil and so on. Okay, and together with the soil organic carbon from the organisms, so we have storing potential. Soils can sequester carbon for about 20 to 40 years before they become saturated. Okay, so we have some numbers also on the right side. So we have like 1 to 13 gigaton of capture, a huge amount of carbon in the atmosphere in an inexpensive way. So we have a good option here. Okay, so these are the environmental and economic benefits of carbon sequestration. So we have greenhouse reduction, biomass displaces the fossil fuel, quantitative indicators about 1.5 gigaton reduction CO2 equivalent per year. Waste diversion, organic waste valorization at about 30% landfill input. We don't want to send the waste to the landfill. We could use it to produce biochar. Soil carbon, biochar plus compost application, soil carbon increases by about 0.4 to 0.8% annually. Then we also have employment. Of course, we're talking about 10 or 15 jobs per 1,000 tons of biomass. Of course, this is variable depending on different countries. And circular economy, we have cascade reuse of biomass streams. We increases the resource efficiency by about 30 to 40%. Okay, so one quick case study. This is the Osaka gas methanation plant, which actually flow of methanation process in Osaka trials. And here we are talking about 1 ton of food waste per day produced methane, and the gas used by 120 households. Annual CO2 reduction, 78 tons per year. This is the pilot scale. So market potential, the CO2 utilization market is projected to grow by about 17% from US 32 billion to US 37 billion. Energy transition package, Japan aims for 90% of synthetic methane by 2050. Cost challenge, synthetic methane is currently 8 times more expensive than the LNG. So this is our challenge and demonstrates circular bioeconomy where the food waste converted to biogas, then methane, and energy for food preparation. This is one case study. Another case study taken is from Malaysia itself, because we have, as I mentioned earlier, 168 million tons per year of biomass, and this produces about oil palm waste alone, it's about 124 million tons per year. Energy potential 2.55 gigajoules, that's about 62% of national energy demand. Electricity is about 5 gigawatt capacity for oil palm waste. Greenhouse reduction 25 to 30 million tons CO2 equivalent. And fertilizer savings 15 to 25% less chemical use with bokashi or biochar. So the potential is tremendous. As I mentioned earlier, unfortunately, we are not actually using the full capacity of the biomass produced in the oil palm industry. Only selected usage is actually taking place in Malaysia. And these are the challenges and limitations on carbon sequestration, financial and economic constraints. I mentioned throughout my slide where the cost is there. High capital expenditure, capex, CCS facility construction may cost about 800 million to 2.5 billion US dollar. And then industrial CCS treatment may cost 500 to 900 million dollar. High operating costs, OPEX is also very high. Poor economic competitiveness and carbon credit market problem. So voluntary carbon markets often value credits such as $5 to $15 per ton, far below the CCS cost. So up to 40 to 60% of nature-based credits globally are considered overrated. So these are the energy penalty and energy efficiency reductions. We have various options, and we need to look for the mature technology and scalability limits on these various technologies which I mentioned earlier. We are looking at long-term storage, integrity, and leakage risk. This is something that also concerns me because sometimes things that we keep in the geological storage may eventually cause problems after maybe 50 years. So this is something that we need to explore very seriously. And then these are the environmental impacts and ecological risks with all these various methods like ocean sequestration risk, ocean fertilization affects phytoplankton, soil carbon uncertainty, biochar limitations, and then forest and ecosystem risks. Measurement, monitoring, and verification challenges. So we need to and measurement complexity and accuracy. We have to be careful about that. Permanence and reversals and leakage. Reporting and verification hurdles. This is still in a question mark of how we don't have a standard way of doing it. Data management integration. And I hope that I've created an impression on the carbon sequestration methods, particularly the importance of biomass utilization in carbon sequestration. So we have carbon and nutrient recycling storage and so on. So decarbonization is a great tool that we can use, especially with biochar synthetic fuel delivery. Green growth emerges through carbon markets, bio industries, and renewable energy deployment. And these are some of my 24 books. And this is my team in my lab. All of them are my PhD students from various parts of the world. Thank you very much.